Acha. Okay. So let us talk about interacting boson model. Boson model. Now you see the shell model, we have been talking about it a lot, right? Now this becomes intractable. Where if we move far from the closed shells, right? So this means that it becomes very difficult to solve the problem, to understand the excitation spectra clearly using the shell model. Basically what I am trying to say is that you remember we have the core states, the valency states and the empty states. Now if we go away from far from the closed shell, then what happens is that this valency space, this becomes large. Okay, and as a result of this we need huge computations. Say for example, you remember when we are considering the simple two configurations for 18 oxygen, we just have two configurations. Now there are cases when there are more than 1 crore 2 plus states in a nucleus, and then we have to do the diagonalization. So basically think about diagonalizing a matrix. Okay, a matrix diagonalization 1 crore by 1 crore. Do you think it is really possible? Of course, we do need, what we need is basically huge computation. But the thing is that just think about it, the number 1 crore by 1 crore. So how do we do that in the shell model? What we do is that we do truncations. We try to get some ideas and then we consider the most important part of the physics so that this matrix can be reduced to a smaller amount, say 10k by 10k, which can be done or something like that. Okay, now there are several truncation ways to do this. Now what I am going to talk about here is yet another approach. Now, so basically this intractability of the shell model when we move far from closed shells, this problem we can circumvent if we have certain alternatives. Now basically there are two alternatives. So alternatives. What are the alternatives? One of the alternative is the geometric collective model. Okay. Here the whole microscopic approach is abandoned in this case, and it is basically replaced by a macroscopic one. Why? Because we are considering collective motion. So why do we need to think about just what one nucleon is doing? We will consider the features of the entire group. So basically what we will do is forget about the microscopic approach and just consider the macroscopic one, involving an assumed or basically deduced nuclear shape. Remember the vibrations, right? With rotation and vibrations about the shape. Now the other alternative is basically algebraic collective model. What is this model? Now basically what the approach is very simple. I have already talked about it. Just like before an examination, you students, you always ask us, sir, which question will come? So the first thing I say, come on, okay, I'll tell you. The first thing I tell you is that no questions will be repeated from the last 2 years. Now this in itself is a truncation to the problem. See, when I am telling you that no question will repeat from the last 2 years, so you will go back, look into the question papers, you will find out which questions have appeared in the last 2 years, and then you will cut it out. But it doesn't mean that the sections, the parts from which the questions have come, it cannot come in a different form. It cannot come in a different way. What I am saying is that those questions will not come. But again, this helps you in getting some idea about what will come in this year examination, right? So this thing is just like the same idea. So basically what we are doing, we are getting some idea and then we are truncating. So what we want is, we want to talk about the most important part and cut off the rest of them. See? So this is the most important part, 10K by 10K, and where the rest of them is cut off. So this is a truncation. Now this algebraic collective model, or basically interacting boson approximation, is an example which seeks to effectively truncate the shell model space in isolating. So the basic idea is truncate the shell model space by isolating the key configurations involved, and this at least in the low-lying states. Come on, you cannot do this for throughout, but at least we should try, starting with the low-lying states, right? So what's the basic idea of interacting boson approximation? Now you see, the basic idea is to assume that the valency, so basic idea is, we assume that the valency fermions couple in pairs only to angular momentum 0 and 2, and that so this is number one basic idea. Number two, you can think of it like that the low-lying collective excitations of medium and heavy nuclei can be described in terms of energies and interactions of such pairs. Now these fermion pairs having integer spin are treated as bosons. See, they have integer spins. So these fermion pairs are treated as bosons because of having integer spin, right? So that's the basic idea. Now you can say in a more quantified way, what are the various assumptions? So the following you can write it down. So assumptions of interacting boson approximation. Number one is that, you see, the closed shell of either protons or neutrons and excitations out of them, they are simply neglected. Now remember, this we have already talked about when I was talking about shell model. So you are not doing something different. The same technique, but in a different jar. Okay, in a different nomenclature. But again the same thing. We are neglecting these things. We are trying to make our life as simple as possible, so that we have to do as much less calculations as possible to get as much better result. So that's our ultimate aim. The next assumption is that the low-lying excitations of even nuclei they depend only on valency space. So see, we have basically core, inert core, then valency space, then empty space. Remember, now what I am saying is that the closed shells and core, they don't take part, number one. Number two, whatever is there, this is because of just this only, and the effect of this empty space and the core space is not there. So this is what I mean to say when I say this. Okay, now let's talk about the next assumption. You see, the valency nucleons they are treated in pairs as S and D bosons. S means 0, D means 2. Remember, with angular momentum, momenta 0 and 2. Now, there are several different forms of interacting boson approximation. Now, we will talk about IBA. Now, what happens in IBA 1? IBA 1 we will talk about. Here, no distinction is made between protons and neutron bosons. They are all the same, and the number of bosons you see is just half the number of valency protons and neutrons, both of which are always counted to the nearest proton and neutron closed shells. Let me write it down. The number of bosons is basically equal to half of the number of valency protons and neutrons, both of which are always counted to the nearest proton and neutron closed shells. Right. Now, you see, this counting rule generates a finite fixed number of S and D bosons. And this finite number, this rule generates a finite fixed number of bosons. And this is important. This finite number has profound effects, and it leads to several predictions that are quite different from the geometric analogues of IBA. Okay. Now, let's talk about the last assumption. Now, the states of this boson system, they result from the distribution of fermions in S and D pairs, right? And thus depend only on the S and D boson energies, and also on interaction between bosons. Now, these interactions are assumed to be simple two-body. Okay. So you see, what we have done is the following. Initially we have got a body fermionic system, okay, having Z protons and N neutrons. Now we are going from here to another system, which is A by 2 body bosonic system. And what I am doing is basically I am replacing the proton and neutron by boson pair, by pairs. So here the boson is basically fermion pair. So this is an approximation. Now the first thing is that here I am talking about only even nuclei right now. Even case here. Okay. So nothing new has been done, the same old thing. Basically we are trying to find the relevant physics and trying to solve it. And so this is basically a truncation scheme. Now you see, previously also when we are talking about the shell model, remember there was a mean field plus residual interaction, right? And this was present between protons, neutrons and all that stuff. Same thing will be here. So here the residual interaction, the interaction right now, let me say like this, that the interaction will be there. So this means that these bosons are interacting bosons. So this means that there is an effect of some interaction. We will talk about it. Okay. Any questions till now? Bolo. Okay. So you see the basic entities. So IBA and the basic entities are the S, that means J is equal to 0, and D, which is J is equal to 2 bosons. Right? These are the 2 bosons. These are the basic entities. Now let us assign them energies epsilon S and epsilon D. This is small epsilon. Okay. Now a given nucleus, suppose let us consider a nucleus which has n valency protons and plus n valency neutrons, right? Here each proton and neutron has been counted to the nearest closed cell. So this will have basically how much? It will have basically NP plus NN. So this is NP, say, and this is NN. So we will have NP plus NN by 2 S and D bosons. Right. Let us take an example of 152 samarium. Here you see capital N is equal to 6 plus 4. Number of proton, number of neutron. And this is equal to 10. Now this is what I am saying here. This is the number of bosons. This is Nn, this is Np, then the number of bosons N is just Nn plus Np by 2. Now here I am written down this N. You check it for yourself. This will be a homework for you. Check it that this you easily find so. Okay. Now remember, no distinction is made whether valency nucleons are particles or holes. And ground and excited states are formed by distributing the bosons in different ways among the S and D states and coupling them to different total J. Now this level structure that result basically depend on these distributions and couplings. Let us consider the simplest situation. Okay. The simplest situation is to imagine all n bosons in S boson state. Right. Then by convention, epsilon s is equal to 0, which is the absolute ground state. Now, what is the lowest excited state? The lowest excited state will be how many? Capital N minus 1 S bosons. Right. Plus 1 boson, 1 D boson. And so what's the energy of the lowest excited state? The energy will be E is equal to epsilon D, since there is 1 D boson. Right? Now, the next excited state, it will have how much? N minus 2 S bosons plus 2 D bosons. Right? So, this means the energy will be how much? 2. Right? 2 epsilon D. Now, have you seen this somewhere? Of course, this you have seen in the vibrational phonon model. So clearly, as in the phonon model, the 2 D bosons here, these 2 D bosons, they can couple to 0, 2, 4. And this triplet, they can couple to J is equal to 0, 2 and 4. And this triplet will be degenerate. Now higher D boson multiplets will also occur up to N is equal to ND. Now this is a purely harmonic spectrum, identical to the harmonic vibrator, except for the limitation due to finite boson number. Okay.